to be the ocean's decade. This is the United Nations Decade of Ocean Science for Sustainable Development. And it's an initiative or plan to bring together scientists, governments, businesses, NGOs to tackle a whole range of problems related to the oceans. Some of the challenges include understanding and addressing marine pollution, protecting ecosystem biodiversity, sustainably feeding the global population, unlocking ocean-based solutions to climate change, increasing resilience to ocean hazards, and expanding the global ocean observing system. An example of one of their initiatives, this is a United Nations UNESCO initiative, is to have 80% of the seafloor mapped, the ocean seafloor mapped by 2030. Presently, about 20% of the ocean seafloor is mapped. They've made enormous progress in the last 3 years or so, bring that number up to 20%, with the motivation that we can't hope to protect the oceans if we don't understand them. So this is a significant UNESCO initiative. Recently, the recent reports from the Intergovernmental Panel on Climate Change, the IPCC, with this one on the left, the Ocean and Cryosphere in a Changing Climate, coming out in 2019, and assessment report number 6 coming out in 2021. This assessment report AR6 was in the news recently because they just published the synthesis for that last month. A big story remains ocean warming. The oceans are continuing to warm, which is having all kinds of effects on biodiversity, coral bleaching, sea level rise, and the list goes on. Melting of glaciers and land ice and sea ice and so on. So with that, I'm going to introduce our first 3 speakers for the morning. The first speaker is Alexey Fedorov. Alexey is a professor of climate sciences in the Department of Earth and Planetary Sciences. Alexey is an expert on the climate dynamics of the oceans and atmospheres and their interrelationships. He's written extensively on topics ranging from El Niño to deep circulation to paleoclimate. He has many awards, and one of his recent awards was the 2019 Presidential Climate Change Research Award as part of our Make Our Planet Great Again program initiated by French President Emmanuel Macron, which is wonderful, and the award fosters Alexey's relationships with French scientists working on climate problems. Alexey teaches courses on the physics of weather and climate, climate dynamics, and physical oceanography. Sorry, I did not switch that slide. So that is Alexey on the left. And then we have Chelly Hull. Chelly is an associate professor in Earth and Planetary Sciences and associate curator in the Invertebrate Paleontology Division of the Yale Peabody Museum. She trained as a biological oceanographer, but works primarily on ancient oceans as a paleontologist and paleooceanographer in order to understand the dynamic coevolution of ecosystems and environments across mass extinctions, intervals of abrupt global warming, and intervals. In 2017, she was named a Sloan Research Fellow in Ocean Sciences in recognition of her contributions to the field. Chelly teaches courses on the history of life and the oceans and marine primary productivity. Next, our third speaker of the morning is Dr. Shimon Anisfeld. He's a senior lecturer and research scientist in water resources and environmental chemistry in the Yale School of the Environment. His areas of interest, which have been the focus of his teaching and research at Yale for more than 2 decades, include freshwater management, coastal ecosystems, and synthetic organic pollutants. And this includes research into the response of saltwater marshes to sea level rise and other stresses. He has a forthcoming textbook also on water management, and he teaches courses in coastal ecology, water management, and organic pollutions, and also a course on the physical science foundations for environmental managers. So those are our three speakers. Thank you very much. And we will begin with Alexey. And I'll just pull up your talk, Alexey.
Hello, everyone. It is my pleasure and honor to be here and to present some of my work and actually the work of many people and collaborators. And I'm going to talk about El Niño, the effects of global warming on El Niño, and generally about changes that take place in the ocean and especially in the tropical oceans. So the temperature of our planet is rising, give or take. We have roughly about 1 degree Celsius of global mean temperature rise over the past 100 years or so. It's relentless. There are slowdowns in this rise, but it's really almost an exponential rise if you're thinking starting from the 1950s. And the warming of the ocean is a big part of it. And this is the plot with one of my former students, Shimon, where we analyzed temperature trends over the past 70, 80 years over the global ocean. And everything is almost anywhere in the ocean you go, it's red, meaning temperature is increasing. If you look at the numbers, talking about degrees Celsius, it's from 1/10 of a degree to maybe 0.15 degrees Celsius per decade. That translates, depending where you are, half a degree, 1 degree, even more in different parts of the ocean. For example, the Indian Ocean is warming faster than the rest of the tropical oceans. The Pacific is warming. There are a few spots on the globe you can find maybe a little bit of cooling, but the dominant signal is this warming. And this ocean warming ought to affect climate variability, different climate and weather phenomena, from tropical cyclones to mid-latitude storms to phenomena like El Niño. And so the focus of my talk on El Niño, also called El Niño Southern Oscillation, which originates in the tropical Pacific. And it's probably one of the most pronounced modes of climate variability on the globe. You go anywhere, you go to Antarctica, you go to the Arctic, Africa, Australia, Asia, and you'll find the signal from El Niño. It's dominant. The typical periodicity of El Niño about 3, 4, 5 years. And once in a decade or several decades, we may have an extreme El Niño events like the events of 2015. And so this is the outline of my talk. First, I will discuss what is El Niño, really. I'll briefly discuss El Niño impacts, then El Niño historical records and past extreme events, and then projections for the future changes in El Niño intensity and the impacts of those events. And then I'll briefly discuss uncertainty, because all our projections have uncertainties, and some of the scientific questions we are working on largely related to the issues of these uncertainties. All right, what is El Niño? If you look at the map of sea surface temperatures in the tropical ocean, you'll find several major features, and one is this so-called warm pool in the Pacific, a very warm temperature, 30 degrees Celsius, 86 or something Fahrenheit, and this is the warmest temperature you can probably find in the global ocean, except for some local seas. And this, in the Pacific, this warm water is maintained by strong trade winds, these easterly winds that keep this warm water in the western part of the basin. On the other hand, in the eastern part of the basin along the equator, the effect of this wind to bring up this relatively cold water, and so there is a strong temperature gradient between east and west, strong temperature contrast, about 6 degrees Celsius. If you look below the surface, what you'll find, the ocean is generally very cold. So below 200 meters, we are talking about temperatures below 14 degrees Celsius. And so in the tropics, there is only this relatively shallow layer of warm waters, talking about 100 meters, where you have this very warm waters. But because this cold water is so close, the winds can maintain this slope of the thermocline, the boundary between cold and warm waters from west to east. And this allows this cold water affecting the surface. And this is why you have this temperature gradient. This is why you have this easterly winds along the equator. So this is a coupled problem. There is a temperature contrast between east and west in the Pacific Ocean. It maintains winds, but the winds maintain this temperature contrast. And so during El Nino, this relationship actually breaks, allowing for a motion of this warm water from the western tropical Pacific to the east. So this is would be neutral conditions in the tropical Pacific with this contrast that I described. And during El Nino, this warm water flows to the east, extending this warm pool during extreme El Nino events all the way to the east. And so the entire contrast between east and west in the equatorial Pacific disappears. So, and this is an El Nino of 1997. This is the strongest El Nino event on record with huge impacts. And if you look, if you check the difference between the neutral conditions and El Nino, it's in this lower bottom panel. There is a huge temperature anomaly in the eastern equatorial Pacific on the order of 5-6 degrees Celsius. This region is called Niño 3, and it's typically used for monitoring and calculating different indices for El Nino. El Nino in Spanish, child, a boy, it's because El Nino typically peaks in December during the Christmas time, and so fishermen in Peru who notice this event, notice this phenomena, they called it El Nino. And then it was recognized that this is not just a warming of the temperature, it's a tropical ocean atmosphere phenomena. The entire thing was called the Southern Oscillation, and then together it's now called El Nino Southern Oscillation, or ENSO. And so this is a warm anomaly can be maintained there sometimes for half a year, sometimes for a couple of years. And you can imagine the Pacific is actually a huge ocean. It's typically the length of the from east to west. If you measure the length of from east to west, it's nearly half of the globe. And so this warm anomaly has huge impacts, not just for the Pacific, for entire global climate, weather patterns. And this works actually as a radiator. During years of strong El Nino events, global mean temperature can increase by a few tenths of a degree. And then after typical El Nino events, the system returns, it overshoots, and there is another state of the system, a cold state. It's called La Nina, with colder temperatures in the east, a few degree colder normally. And that's the oscillation between El Nino and La Nina, and it repeats with this periodicity of 3, 4, 5 years. We have an extensive array of mooring stations in the tropical Pacific since the 1980s. where we monitor how El Niño develops. And this is a very important tool for El Niño prediction, because this array provides data from the ocean subsurface for prediction, for El Niño prediction that can go for half a year to a year now. And this is a typical mooring with a buoy and various sensors measuring temperature and winds and other climate variables. And this is an example of a deployment of this buoy. At the same time, we can monitor El Niño development from space. And this is just an example of the latest extreme El Niño event in 2015. And if it works, you see the development of this very strong El Niño. These are temperature anomalies. And by December, you see a huge extended temperature anomaly here. Yeah, and this is...
Ooh, you should definitely, there's a good highlight. Yeah.
Right.
So we're just.
All right. Yeah, okay. So, well, it's impressive, I can tell you. And just to talk a little bit about the physics, as I mentioned before, it's a coupled ocean atmosphere phenomena. It couples trade winds, the ocean thermocline, this boundary between cold and warm waters. And during El Niño, there is convection over the warm pool, so it's air rising, so convection moves to the center. Trade winds relax, the thermocline deepens, and you get this warm anomaly in the west. During La Nina, the system goes back, trade winds strengthen, and you have stronger upwelling of cold waters, so more colder waters coming to the surface, so stronger temperature gradient, stronger trade winds. And so that's the oscillation between El Niño and La Nina. As I mentioned before, the most frequently used index for measuring ENSO, El Niño, is this the Nina3 index. So it's temperature anomalies over that Eastern Pacific, Equatorial Pacific region. And this is a time series from instrumental observations for about 140, 150 years. And you can see this irregular cycle with warm events and cold events. And the last three strongest events in the observational record, 82, 97, and 2015. The 1997 event was the strongest, with some $30 billion of damage just in the United States alone, and thousands of lives lost globally due to floodings and other extreme events. If you look at the magnitude of events, so some average magnitude, some standard deviation, if you wish, and so El Niño was weakest in the middle of the 20th century, with a typical amplitude, mean amplitude of about half a degree. And the strongest events happen in the 80s and the 90s, so it's the peak of El Niño activity. And so these two events corresponds to this peak. Since then, the amplitude reduced slightly, but it still remains at a pretty high level, exemplified by the 2015 event. And obviously, with the three largest, strongest events occurring during the last 50 years, when CO2 has been pumped into the atmosphere with a high rate, the question arises, well, these extreme events, is it what we should expect in the future? And so the question whether this strengthening of ENSO will continue or maybe not remains a very important question of climate sciences. And I've been working on this question with my postdocs and students for quite a while. And we have a good handle on that, but there are still many uncertainties, and that's what I'm going to talk next. But before, still would like to discuss some impacts. And I like this two pictures. It's from El Nino of 2009, 2010, a moderate El Nino, nothing special, but you can see some of the impacts. So this is in Australia, so drying lake. I like the sign here, no swimming. Well, you can try, but nothing. And on the other side of the Pacific, in Southern California, floodings, mudslide, heavy rain. That's a very typical signature of El Nino. 2015-16, many different things, but the most prolonged, the longest coral bleaching event, February 2016, global tropical phenomenon. Coral bleaching is a big problem, and it's really gets worse during El Nino events, and this was the worst event in recorded history. Going on to India, typically, not always, but typically it's a weaker Indian monsoon, and that has strong impacts on agriculture. And so actually the relationship between ENSO and the Indian monsoon was how the Europeans discovered the Southern Oscillation. Hilbert Walker was sent by the British to India to investigate the reasons for the failure of monsoons. And so he established this connection to the Southern Oscillation. And later on, it was recognized as part of the ENSO cycle. And this is just a general map of impacts. The strongest impacts are in the tropics, from wet to warm to drying. But the impacts extend all the way to North America and Southern California, for example. Typically, not always, again, experience wet winters and during El Nino events, relatively wet winters. And this is related to the ability of El Nino to generate the so-called teleconnections, atmospheric planetary waves that shift the position of the jet stream. And so the jet stream shifts southward, and this is how we get this wet winters in Southern California. All right, so these are impacts, just a few examples. So it is important. And so predicting the future of El Nino is important both from scientific perspective and a practical perspective. If indeed extreme events become more frequent, this is something to take into account in planning, in socio-economic predictions. And so that's an important issue. And so climate modeling, it's quite a developed part of climate sciences now. We have many state-of-the-art climate models, and the idea is to use differential equations of motion, Navier-Stokes equations, on various grids for the ocean, the atmosphere, land, and the interface. And various processes connecting the ocean, the atmosphere are described by those models, from clouds to deep ocean circulation, to processes on the interface, sea ice, everything that you can think about. And climate models are pretty good now in simulating El Nino, and this is just an example of a time series generated by the Community Earth System model, version 1, CSM1, with El Nino events and cold La Nina events, with a nice periodicity, more or less realistic amplitude, and these simulations can be conducted for centuries. They can be conducted for future climate, and you can compare different models as well. So the issue of El Nino of global warming, obviously, it's not a new one. And actually, at the start of my scientific career, one of the first papers I published with my then postdoctoral advisor, George Philander, was, "Is El Nino changing?" So that was in the year 2000. I just picked up several papers from the recent few years discussing that. And I just highlighted here, increase ENSO, robust decrease in ENSO, weakening of ENSO. So that's where we are in general, even though I think this is maybe a little bit misrepresenting the consensus. I still think the consensus is that El Nino is indeed changing, and it's changing towards stronger El Nino events. And that's what I'm going to show next. So with my former students, Ulla Hidi, we analyzed a bunch of models from the so-called coupled model and comparison project, phase 6, CMIP 6, which is part of an IPCC process on climate model intercomparison and climate projections. And some of the experiments, they produce its experiments with different future, what's called shared socioeconomic pathways, SSPs. So different scenarios with different CO2 emissions. And I just provide several of them here in this plot. So one is very pessimistic with CO2 getting to a level of something like 4 times pre-industrial in the end, and somewhat optimistic with CO2 rising and then slowly decreasing. And so we analyze these 2 sets of experiments for different models, plus other experiments. And these are the results of these different models, quite a few of them. So the black column here, black columns here is the control climate, historical climate, if you wish, and several experiments. So red is this pessimistic scenario, purple is more optimistic scenario, and several other types of experiments. And there are variations among the models, but if you look and compare them together, the signal is quite robust. Multimodal mean produces strengthening of ENSO by the end of the 21st century, regardless of which experiment we consider. Optimistic scenario, pessimistic, increase in CO2 levels by a factor of 4. There is a general increase in CO2, in ENSO amplitude. We are talking something like 10 to 25% increase, which is a moderate increase, but if you try to analyze it further, you find that it translates to a much greater increase in extreme events. And really what we care more, it's extreme El Nino events. A moderate El Nino events will have a signature in weather patterns, but it is not going to produce huge damages, changes in hurricane intensity or floodings, a little bit here or there, but it's okay. But the extreme events, this is what we really care. And this analysis suggests, again, regardless of experiment we considered, we expect 20 to 100% increase of extreme events. So we are talking about half event per decade extreme event in historical climate to about 1 extreme event per decade. And that's quite a strong signal. So 82, 97, 2015. So these are 3 extreme El Nino events we had over the past 60 years or so, even longer. And this would mean having an extreme event every decade. That would be quite a big change. And more importantly, what we analyzed, the intensity of rainfall changes associated with those events. Why rainfall? Well, rainfall is important because a large fraction of heating that El Nino provides comes from condensation of water vapor in the atmosphere, and that's the so-called latent heat release, and it's directly proportional to precipitation. And so climate impacts, remote climate impacts directly related to the amount of rainfall. Obviously, flooding events as well, but impacts of El Nino, it's largely connected with rainfall. And with rainfall, we see 30 to 100% increase in rainfall variability associated with ENSO. So a stronger rainfall by 100% means a factor of 2 increase in impacts or even more. And the physics for this is pretty simple. It's the famous Clausius-Clapeyron relation, which allows the atmosphere to hold more water vapor with warming. And if the atmosphere has more water vapor, when rain happens, rain becomes stronger. And that's as simple as that. And so this is a huge signal. And again, it does not depend on the model we considered. Every model shows this. Doesn't depend on the experiment. And that's a really strong signal. The next thing, talking about physics, why should we expect a stronger El Nino? Well, besides this issue of rainfall, one thing model predict this enhanced warming of the eastern equatorial Pacific, mean warming with climate change by the end of the 20th century. So there is a general warming everywhere. We're talking about an order of 3-4 degrees general warming of the ocean, but then roughly 5 to 6 degree warming in the eastern equatorial Pacific. And with this warming, in simple terms, it's easier for El Nino to develop. The eastern Pacific is already slightly warmer compared to the west, and so that helps El Nino to develop. And the second thing, it's actually related to tropical cyclones that occur in the tropical basin. And so part of El Nino cycle is the so-called westerly wind burst. Without really explaining what it is, there are these bumps, and these bumps associated with wind anomalies that occur in the western equatorial Pacific. This part of a relaxation of westerly winds, and in turn, this burst associated with this hurricane-like structures, tropical cyclones that develop close to the equator. And there is another example from satellite photos. There are these pairs of tropical cyclones in the vicinity of the equator, and they generate those wind bursts. And so we analyzed the probability of this burst with warming, and we predict an increase in intensity of those bursts by 1 category. You can think about stronger tropical cyclones affecting El Nino in this region. And so this factor contributes to the future strengthening of ENSO. I have to talk about uncertainties because, as I mentioned before, the consensus is that ENSO is going to be stronger, El Nino events going to be stronger, impacts will be stronger, but there are models that disagree with that. There are scientists who disagree with that. So I need to talk about uncertainties. And one of the uncertainties concerns recently observed trends in the tropical Indo-Pacific. So this is what the models predict for the end of the 21st century. But these are trends for the last 40 years. And you see the warming almost everywhere, but actually in the east, close to South America, there is a slight cooling. And that's an interesting phenomenon, and it suggests a possibility of a transient ocean thermostat. So with strengthening of CO2 forcing, the ocean responds actually stronger in the west than the east. And that may lead to the strengthening of trade winds, which would keep this water relatively cold. And actually, it's quite interesting. If you look at Nino-free records, so this index of ENSO for the past, since the 1980s, there are ups and downs, warm events, cold events, but the baseline is basically flat, while global mean temperature keeps increasing. And so this is one of the probably most intriguing problems in tropical climate dynamics right now. Why global mean temperatures, why with this global mean temperature rise, the baseline for eastern equatorial temperatures in this region doesn't really change. And so again, this is suggestive of some kind of ocean thermostat. With Ulahidi, who I mentioned already, we showed that this thermostat can be transient, and eventually it will shift towards a warming in the east. But for the present time, there is no real warming in the east. And we actually had experienced a 3-year-long cold La Nina event, which actually came up as a big surprise. So this near the end. So 3 years of cold La Nina conditions, which is quite unusual. And predictions for this year. So there's a prediction from a bunch of models. Predictions are towards El Niño conditions. There is huge uncertainty from some models predicting almost nothing, with some model predicting a 2 degrees warming. Overall, models predict a moderate El Niño event. Again, no extreme events, just a moderate event. We'll see whether these predictions hold, but this is where we are. And the last piece of uncertainty that I want to emphasize, for the long-term prediction of ENSO, we still have a lot of work to do. These are just 3 models, and each column here reflects ENSO amplitude for future projections go into 1,000 years. It's maybe not really important in practical terms, but it is important for me as a climate modeler. And each column describes 200 years. And so some models predict stronger El Niño in the future. Some models predict very flat, and some models predict a demise of El Niño. And so we still have to resolve this to be absolutely certain that the models perform the way they should perform, and to make sure that our projections for the end of 21st century are robust and valid. That brings me to my summary. Despite all these uncertainties, I think very likely with global warming, El Niño will become stronger. In terms of temperature anomalies, El Niño impacts will be stronger. It's very likely. It doesn't depend upon models, doesn't depend on climate scenarios. Even if temperature amplitude of El Niño does not change, the impacts will be stronger. That's very likely. It's a very robust. There are still uncertainties, and hopefully there is still plenty of work for climate scientists, for students, postdocs. So there's plenty of interesting topics to discover, and plenty of interesting phenomena to discover. So it's an interesting problem. It will be a big problem for years to come. And so I think with that, well, thank you for your attention.
I have a question regarding the teleconnections map. Do you think this is like an exhaustive map, or is that simply reflecting of where people have looked so far? And if El Niños become stronger, are there any, would you expect new teleconnections to also pop up?
So let me start with the end of your question. So I think this map, this general map is not going to change, because the dynamics of this teleconnection is pretty robust. It's changes in atmospheric circulation along the equator, and teleconnections to mid-latitudes associated with the shift of the jet stream in the northern or southern hemisphere. So that's pretty robust. And so most of these connections will remain the same. The strength of anomalies in precipitation or drying will definitely increase. And we actually see it in Australia. droughts in Australia with El Niño, associated with El Niño events, have increased even in the past 50 years. Some of the variations in this teleconnection happened because of different types of El Niño. So I was very general, but each El Niño is unique, and sometimes you have strong El Niño events closer to the very east of the equatorial Pacific, sometimes closer to the central part of the Pacific. And so there are slight difference in teleconnections. For example, if El Niño happens in the very east, it has strong connection to Southern California. In the central Pacific, not so much. And so depending upon these variations, you may have some differences in teleconnection. But overall, the patterns are pretty robust. And so I don't think they're going to change. Again, each El Niño events can be unique. For example, the failure of monsoons in India happens with some El Niño events, but not with other events. So it varies. But again, I think in general, teleconnections are pretty robust.
Do you mind pushing the button on your? Yeah, thank you.
Thanks, Alexey. You mentioned the sort of thermostat behavior of the Eastern Equatorial Pacific. I wonder, is there a sense of sort of what threshold of warming you need to achieve for that thermostat to be broken, to move it to like a new baseline state? And once you get to that new baseline state, does that quickly cause an abrupt change in the sort of amplitude of El Niños?
We investigated with this phenomenon in a couple of papers, and it seems like it's not a threshold behavior. It's rather the rate of change of CO2 in the atmosphere. If the mechanism of this thermostat is relatively simple. So you increase temperature in the surface ocean because of the radiative effects. And the West warms more, the Western Pacific warms more because there is upwelling, so cold water coming to the surface in the east. And so with West warming more, there is actually a strengthening of easterly trade winds, and that cools the eastern part. So that's this seesaw effect or thermostat effect. For this effect to end, you need to warm subsurface ocean. And that takes time. We're talking about something like 40, 50-year time frame. And if you keep rising CO2 very quickly, the ocean, subsurface ocean, we're talking about ocean at depths of 50, 100 meters, does not have enough time to warm up, and you have this thermostat. But eventually, the subsurface ocean will pick up this warming. And so in the majority of the models, what we see, between 30 years to 80 years, this reverses, and the Eastern Pacific catches up in temperature, and you get a warming, what you expect. So the enhanced warming in the Eastern Tropical Pacific. And so the thermostat is not acting anymore. So not really a threshold, more like the rate of change of CO2 and how long it takes for the ocean to catch up with that.
Do you have a sense of like if that once that gets reached, is the change in El Nino more abrupt at that stage? Then does that flip a switch?
I don't think there is like an abrupt change. It's more a gradual change. It can come up as an abrupt change because you may have a decade of relatively weak El Nino events, and then suddenly the next decade you have two strong extreme El Nino events. And that will be like an abrupt event. But really, it's more like a statistics where you have a gradual change and then suddenly you see this strong events. Yeah, but I don't think there is like a tipping point there. I think it's more gradual changes. But when they come, you'll see the effect. So that's, and some of the events, what we see is, again, there is a huge question. The events of the past 40 years, 82, 97, 2015, is it really related to global warming? We don't know. We don't know. So.
Well, it's really nice to be here, and it's always quite something to follow on Alexey. I'll get back to Alexey in a minute, but he and his models are pretty darn good. So today, for my talk, I'd like to focus on using ancient oceans to infer what may or may not be the limits to what life can adapt to under warming climates. And just to get us started, I'm going to introduce an idea that I know will be coming up quite often this afternoon. I've peeked ahead at some of the upcoming talks. But essentially, for those of you who perhaps don't work on living organisms or don't think about living organisms as much, a key thing to know is that temperature really matters for life. Everything has a temperature range that it can survive in. You know, you put us on the surface of Antarctica without a coat, we don't last very long, right? So once you exceed those limits, abruptly, the organism can die, but populations as a whole have an even narrower range of temperatures that they need to be in to thrive. And so one of the major questions we have in a warming world is, okay, as the world warms, what is going to happen to all of the living organisms? Because as a organism-focused person, it's not 2 degrees of temperature that really matters. It's what those 2 degrees of temperature do to the environments that we depend on. It's what those 2 degrees of temperature do to the organisms and the ecosystems that we depend on. And here I'm showing you a bluefin tuna, a Pacific bluefin tuna. And this is a species that's Curtis Deutsch is a marine physiologist and climate modeler that's at Princeton, and the bluefin tuna has been identified as a species that's particularly sensitive to the warming ocean. And bluefin tuna, like many organisms in the ocean, they can't simply move to follow their temperature niche. There's actually an interesting interaction that happens between things like temperature and things like oxygen in the ocean and things like productivity. And so it's the interplay of these different factors that actually affect what an organism can do in response to warming temperature. Now, when modern ecologists and physiologists go out into the world and they look at the thermal tolerances and the ability of species to deal with warming, one of the surprising things that they've found really robustly in across the ocean and on land is that tropical species appear to be right up against their upper thermal limit. So when ecologists go out and they measure what organisms can tolerate in the ocean and on land, they say, oh my gosh, if it gets 2 degrees warmer, it looks like everything is going to die. And that's really, that's really worrying, right? Things that are in higher latitudes, they have a little bit more wiggle room and they could always move. But things that are in the tropics that are right up against their thermal boundaries, this is of a big concern. What will be in the tropics if it gets a few degrees hot? And so to make this a little bit more concrete, it might be helpful to think about ourselves. So we are endotherms, right? Like we're warm-blooded organisms. And so for us, mammals and birds, it's not just the absolute temperature that matters. It's the temperature plus the humidity of the air that matters for dissipating heat. So our body is working to keep an internal temperature constant. And if we're not able to dissipate our heat, we actually cook ourselves. So that's the first stages that's heat stress leading to heat stroke and death. And it turns out that humans and mammals, we lose most of our heat through evaporation. 75% of our heat on average is through evaporation. So for us, a map of just temperature isn't the most pertinent. For us, what matters most is temperature plus humidity. And that's what you're seeing here in this map. So in this map, you're seeing what's called wet bulb temperature. And I don't know how many of you guys were old school and like took the thermometer with the cotton wrapped around it and swung it around your head. How many people did that? Anyone? Oh my gosh, it's like so fun. But if you do it, that's actually how you measure wet bulb temperature. And so you're actually looking at how much moisture can evaporate for a given amount of time and how much that evaporation, that's telling you how much water can be taken up by the air, how saturated the air is, and what that combined with temperature is. And so this is the wet bulb temperature map of the Earth. And this is showing you maximums accumulated over about a decade. This is from a paper by Sherwood and Huber in 2010. And this map is really interesting because I'm from Central Ohio. And being from Central Ohio, I always thought in the middle of the summer, it was so hot I was going to die. And like, it actually turns out that Central Ohio in the summer is not that different than the tropics. So this is a surprising map in many ways, but it's just telling you that areas, if you combine temperature plus humidity, you get a different perspective of what we might consider potential for heat stress across the planet. The other thing I want to take away from this modern map is that nowhere on the planet is much more than sort of, yellowy orange at most, which is around 32 degrees wet bulb temperature. And it turns out that for mammals, if you get much above 32 degrees wet bulb temperature, and particularly for humans, we die. So you can't get right up against the absolute limit, which is around, closer to 34, because your rate of heat dissipation, you start to slowly cook yourself. And exactly how that happens depends on your age and your physiological condition. But we do know that this boundary somewhere between 32 and 34 is right about what we can survive if we're exposed to the ambient temperatures. So this map in some ways reinforces this idea, right? If you warm the global world by 2 degrees, you're going to push lots of these areas above what we think us personally, humanity, can survive, and all of those other endotherms that we might worry about, all the birds and mammals. So this, gives a lot of room for concern. And furthering this perspective, we know already that all the nasty things that the climate system can do, and we've certainly been seeing a lot recently with atmospheric rivers and flooding and hurricanes. Don't get Alexey started on hurricanes. So we just saw a great talk on that yesterday. There's a lot of dramatic events, but heat stress is actually a major killer globally, and it's projected to be a major killer in the coming centuries. And it's a massive, massive issue for societies around the world, leading to things like global geopolitical instability. So this is a big deal. And so there's really this big question: is it possible for life to adapt to a world that's on the surface a couple degrees hotter? And as a paleontologist, which I am, I always find this really puzzling, because I'm like, wait a second. If we look back across the history of just the last 100 million years, I'll walk you through this plot. So this is the present day up here. This is 100 million years ago here. This axis here is basically showing you a measure that we have to estimate temperature in the bottom of the ocean. I'll get into that in a second. And what you tell is that the present day right up here, although the climate's warming, it's actually much cooler than it's been pretty much any time in the last 100 million years. And in fact, we think over the last 100 million years, the Earth on average has gotten something like 12 degrees Celsius cooler. We've had this long-term cooling that's been going on. And there's certain highs. So like right around 95 million years ago, it's super, super hot in the Cretaceous. And then in the Eocene, right, when a lot of our mammalian ancestors were really going nuts, it was also super hot. But the overall trend is towards cooling. And this temperature measure we get, we can't actually, of course, go measure temperature directly in ancient oceans, and so, or on land. So in order to get an idea of what the whole world as a whole is doing, we actually try to trace the temperature of the bottom of the ocean. And the reason for that is, as you guys probably remember from elementary school, the water in the bottom of the ocean is all about the same temperature. So you can just measure it anywhere. And that's helpful if you're looking in the fossil record, because you can't always get a fossil from the same place through time. And you get more or less an idea of what the bottom of the ocean temperature is through time. And so since we can't actually use a thermometer, we use what's called a proxy, something that we think approximates what we care about, in this case, temperature. And delta 18O is telling you the isotopic composition, the relative heavy to light isotopic ratios of calcium carbonate in the bottom of the ocean. And so that's how we trace temperature. But that's the bottom of the ocean. And we actually know that the deep ocean temperature doesn't really tell us exactly what the surface temperature is. And the reason for that is that you can think of the ocean and the atmosphere as equal partners in the climate system. Both the ocean and the atmosphere are working to move a lot of heat from the tropics towards the high latitudes. And because of that, as the temperature changes, as you have this, sorry, I gotta go back now. As you have this 12-degree cooling, the amount of energy that needs to be moved changes. And so we actually think that in relatively warm climate states, the relative temperature gradient between the low latitudes and the high latitudes is different. But how different? That's the question. That's what actually we need to know if we're gonna say, how hot was it in low latitudes? How hot was it in high latitudes? And it turns out that it's actually really hard to measure temperature. This is what we've been doing as a paleoceanographic community the most for the last 30 or 40 years. We just go out and measure temperature all the time. When I was a student, I was like, my gosh, this is so boring. Like, somebody is showing me a few more isotope plots. Like, I don't care, right? But it's because it actually turns out that all these different proxies disagree. They disagree for important reasons that relate to how these different measures record temperature. And so here we are, 40 years, 50 years after we've been doing this, and we still, are struggling to answer this question. And so in my talk today, what I really want to get into is ask the question, so how hot has the surface temperature been? And I'm going to make the argument that we actually right now are able to answer this question after decades and decades of doing it. There's the data there, and there's the diversity of approaches to do it. And then I'm going to give you a hint about, and how did life respond? Mostly going to give you a hint about it because I have a wonderful incoming YIBS postdoc who's going to be working on that some more. And because, as you guys might already imagine, this is a really, really big question. We could talk about this question for a semester, not for 30 minutes. So I'm going to focus most on what we can learn about how hot the surface was from oceans in the past. And of course, I'm talking about this from the ocean perspective, not just because of the utility of the ocean, the deep ocean for measuring temperature, but because we, of course, live on an ocean planet. We live on a planet that by surface area is mostly ocean, 70%, but by volume, habitable volume is by far mostly ocean, right? Most organisms on this planet have a total different perspective of what it means to be an earthling. And on top of that, it turns out that the ocean is a great place to go if you're a geologist and you like to look at fossils, because things wash away from land and they end up in the ocean. So when it comes to continuously deposited archives that can tell us about the past, the ocean is really a phenomenal place to go. I still remember during my sister's wedding, she and her husband, they really love the mountains, and they were standing there and they go, "Our love is like the mountains, it will last forever." And I was sitting there, I was like, no, like, no, the mountains go away so fast. It's the ocean that's there forever. So anyway, fossils, bottom of the ocean, it's the easiest place to be if you want to trace what's going on with the climate system. So it's not just because it's big. It's not just because it's part of the climate system. It's because there's a lot of sediments down there. Now, of course, the ocean is deep. So if you want to get these fossils out, you actually have to take out a drill ship. And this is a technology that we actually pioneered here in the United States way back. It was like a brainchild in the late 1950s as a parallel to the moon, to racing into outer space, the moon race. It was also racing to explore the bottom of our ocean. And we started ocean drilling in 1961, and we've been scientifically ocean drilling ever since. And what this requires is getting a boat that can actually stay in one spot on the ocean, which is a really fancy trick. It has all these motors over it, and it shimmies and tries to stay in one spot. And then you have this huge derrick, which actually pulls up a drill pipe and actually allows you to put drill pipes together to reach kilometers, sometimes 4 kilometers from the boat to the bottom of the ocean, a distance which is so great that the pipe, even though it's like metal, actually bends and waves on the way down because it's such a long pipe before it actually hits the bottom of the seafloor and drills into the sediment. Now, the sediment itself in the middle of the ocean is oftentimes made up 100% of fossils, because far away from land, there's not much dirt, right? So it's crazy. You go out to the middle of the ocean, you put down this long spaghetti string pipe, and you can drill kilometers of sediment. And that's what you're seeing here. This is a part of a core coming back up on deck on a cruise that I was on over a decade ago. This was actually the first section, so we were really excited. And in those, the reason why it's sort of light brown is because it's almost 100% fossils to tell us about the past. And this is what it looks like once the core has been split. This actually happens to be from a really important transition. This is actually coming from the Cretaceous Paleogene mass extinction, which is an extinction that I care quite a bit about. And after 50 years of drilling, we actually have huge libraries of cores in 3 different places of the world where we can go to pull out sections from different parts of the world's oceans to ask questions. So when someone tells you what the temperature was, most people, if you ask them, how do you know what the temperature was 10 million years ago? Almost everybody will say ice cores, right? Everyone will be like, oh, you look at the gas trapped in the ice. The ice that we drill is it's less than a couple million years old. You always are actually going to these cores to figure this out. And we're actually figuring it out using these organisms, planktonic foraminifera, oftentimes for the surface ocean, and benthic foraminifera for the deep ocean. These are microscopic. I meant to bring models. I'm so sorry. I'm so forgetful. I usually forget my keys. And so these are about the size of a grain of salt. And if you take a little teaspoon and you scoop out a little teaspoon of sediment, you can get millions of these fossils in there. Their different shapes reflects different species with different habitat preferences. So we can pick out individual fossils and then actually measure the different geochemical composition, the chemical composition of those fossils to tell us different things about the ocean environment. Temperature, we can talk about acidity, we can talk about productivity. So we can really reconstruct what the past environment looked like using fossils from the deep sea. And so planktonic foraminifera, oh, I didn't even tell you what they are. Single-celled protist with a shell. That's one way that we reconstruct past climates. And one of the things that we measure are the ratio of oxygen held in its calcium carbonate. We can also measure something like the amount of trace metals incorporated into it. I didn't write it here, but another major proxy is magnesium calcium. And another major proxy we use is something called clumped isotopes. It just tells you how often in that calcium carbonate do you find a heavy carbon paired with a heavy oxygen. And that clumping has to do with essentially how slow the molecules are moving and how likely they are to sort out by heavy, heavy and light, light. So these proxies are all very physically based relative to temperature, but they're all biased by different factors. Delta 18O equally strongly records changes in salinity. Clumped isotopes is super sensitive to changes in preservation. Magnesium, calcium, it's got its own issues. You have to know what the water's doing. Same thing with Delta 18O, it's a nightmare. So for that reason, people continually develop new ways of measuring temperature from the deep ocean. And one of the other ways that people measure temperature from the deep ocean is using biomarkers. And the best way to understand biomarkers, if I were a real biomarker person, I'd get up here and tell you about the molecular structure, but I'm not. So instead, I want you to think about a stick of butter. And if you have a stick of butter and you leave it on your counter in the summer, it becomes like this mushy puddle. And if you leave it in your refrigerator, it's a hard stick of butter. That's because you're right on the melting point, basically, of those lipids, right? Like it gets a little bit too warm and they essentially are melting apart. They're no longer solid. Now, every organism on this planet, we all have cellular walls that are basically made out of lipids, out of butter. And so if you're floating around in the ocean, the last thing you want is to get into a cold patch of water and turn into a hard stick of butter or a hot patch of water and melt, right? You can't afford to do that. And the way that organisms deal with this is by changing different structures inside their lipid membrane walls. So they basically add extra structures to keep the fluidity of their membrane wall constant under different temperature conditions. So when we go into the sediments, we can actually look at the ratio of those membrane structures in order to make an inference about what temperature was. And so there's two main biomarker proxies that we use for temperature. And I'm going to talk mostly about one called TEX86 today. This is from the membrane lipids of archaea found in the ocean. And sorry, I missed the key point. I got so excited talking about proxies, just like all those people. So the key point is that after 50 years of a lot of proxy development, we now have multiple different methods of measuring temperature. They all have their own biases, but if we measure them all at once and we look at them all at once, we can put bounded uncertainty on what temperature change was. And so what my group set out to do was to put all the different proxies together so we could put error bars on our knowledge of past surface temperatures. I don't think we will ever know exactly what temperature it was, but we will know within some confidence bounds, as Alexey was talking about yesterday. Within uncertainty, we'll have some estimate of what's going on. And so within uncertainty, we can have confidence bounds of what temperature did on the surface in the ocean through time. And so what I'm going to show you mostly is work from a former graduate student of mine, Daniel Gaskell, where he did this looking at the delta 18O of surface dwelling, so that's the planktonic foraminifera, over the last 95 million years. So this goes from zero, I have to walk around, 0 to 95 million years ago here. And he compiled the data from 151 different studies. I had to go look at the table again. This is something like more than 23,000 measurements of the stable isotopic composition of a certain species. So just to put that in perspective, for each one of those 23,000 measurements, somebody spent at least 2 hours of their life generating it. So it's a lot of time that's gone into this compilation here. And you can separate that data out from all around the oceans. You could look at where it is, relative to ocean basin. You can look at it relative to the low latitudes. Here we roughly call the tropics 30 to 30, mid latitudes, so anywhere in between 30 and 60, and then the high latitudes, anything above 60 degrees. And you can start to actually take into account all the biasing factors that matter for inferring temperature. Now I'm going to skip all of the technical details of what we did to get temperature out of this compilation. It's why it's a PNAS paper. We basically did a lot of complicated stuff for dealing with changes in preservation. We accounted for things like changing salinity through time. We accounted for differences in ways that people actually align at delta 18O to temperature. So how you calibrate the proxy. And we actually excitingly have a paper that's in press right now in Climate of the Past with an online tool hosted through the Peabody Museum, where you too can do exactly the same thing with any of your data sets now. So that's exciting. So we've hopefully enabled other people to do this. But once you filter out all the data points that we think have poor preservation, and once you just focus on the ones that are really good, you get a curve that looks something like this. So this up here in the yellow orange, this is the 30 to 30 degrees latitude data, and down here in dark blue and in light blue, that's the high latitude data, about 60. And we only kept the very, very best data points for this analysis. So those are actually only on the top line. If you focus on that, these are those orange data points. And then that means that there are long periods of time where we have relatively little data. So we actually looked at the relationship with the good data points between the good data points and the high latitude temperatures, and used it to interpolate the record. You can also, all of our analyses were also done on the uninterpolated, but the curve itself, the yellow bit, is the interpolation of the orange data points. And what you probably notice is it's not just orange data dots. There's actually some other colors up here, and those are some of these other temperature proxy types. So clumped isotopes, it's really hard to measure. It takes a lot of sediment. So there's just a very few data points scattered around from clumped isotope measurements. And then we have one of the biomarkers, UK37. It's a really good one. It's the gray shadow here behind the most recent data. And what you can see is they more or less agree. And that's true in the high latitude, in the low latitudes, and in the high latitudes. And most promisingly, we actually reconstruct the modern temperature correctly. That actually oftentimes doesn't happen. So our modern temperature estimate is 26 for this latitudinal band and about 1 for the high latitudes. And that's right at where it should be, with our global mean sea surface temperature of 17 today. And so what we can do with this is we can actually say, in the low latitudes, how much has temperature changed over the last 95 million years? And what we see is that based on delta 18O, we estimate that low latitude temperatures have changed by 10 degrees Celsius over this time period. And at high latitudes, it's something like 15 degrees, which gives us this global deep sea temperature change of about 12 to 13. So this lines up, but it does tell us that in these low latitudes where modern estimates say 2 degrees should kill everything, we know that it was at least 10 degrees Celsius hotter in the past. And what's more, it is worth pointing out that, even during the Pliocene, which is about, let's say about 4 million years ago, temperature estimates are about 4 degrees hotter than the present day. And, this is when our ancestors were doing quite well in low latitudes like Africa, right? There's a lot of things found in these latitudes. And when it's, 4 degrees hotter, so hot, more than a few degrees. So that work, all of this work gave us the ability to actually calculate what this latitudinal temperature gradient is, so how the whole climate moves energy. And that work is already out. So what we've been working on in the meantime is actually doing the same thing, but for Tex 86. This is one of those biomarkers. That's in the red line. Now, Tex 86 has always been known to do some wild things in deep time, but we wanted to use this to bound how well do we know or don't we know what's going on. And what you see is that the red line, Tex 86 is in red, and our Delta 18O record that I just showed you is in blue. And you can see that towards the recent day, they converge, which is always promising for a proxy. They're tuned toward the modern day, so they should converge. But you can see as you go back through time, this is, again, this 30 to 30, 30 north to 30 south. They're generally in the same realm, but they're actually diverging most at the warmest parts of the Eocene and in the Cretaceous. So that's where our greatest uncertainty is in temperature estimates. But Delta 18O is giving us the lower bound. So it changed by at least 10 degrees, but perhaps by as much as like 14 or 15 degrees hotter than the present day. And so you could, in all the other data points, the magnesium, calcium, the clumped isotopes, and they actually fall somewhere in between here. So these are sort of like the bounds on what our uncertainty is through time. And so this allows us to really say for the first time, like what our confidence is in sea surface temperatures through time and what our uncertainty is as you go back, what the error of uncertainty is as you go back through time. Oh, sorry. And I didn't mention all my people here. So Daniel again did the Delta 18O curve, and Gordon Inglis and Charlotte O'Brien are experts in biomarkers, and they have been working on the Tex 86 part of the compilation. And so what we can do now, once we have estimates from the surface of the ocean, is we can start to talk about what heat stress is doing through time. So we can actually move from the isotopes, which again, it really took me decades to actually be like, okay, I can measure an isotope without being bored, but we can move from the isotopes back to what it's doing to life and what life is doing in response. And so we can start to think about heat stress through time. And when we first thought about this problem, we decided that we were going to focus on heat stress on land first. I'm sorry, oceans. But in the oceans, it's complicated because of the interaction between temperature and oxygen on the distribution of organisms. And we actually have a much harder time of constraining oxygen. So we're focusing first on heat stress on land, particularly also because it pertains to humans and our societies. And so we wanted to say, what is terrestrial heat stress through time? Now, it turns out that you can actually do this just by knowing the ocean alone. There are wonderful people who go out and measure temperature on land, but it's even harder to do on land and even more uncertain. Allison can tell you all about that. We really try on land, but it's even more tenuous. So it's easier to measure it in the ocean and project it onto the land. And we can do that thanks to atmospheric dynamics, about which I know very little, but my colleagues do. So Matt Huber is a climate modeler, and this is his postdoc, Quinn Kong. And essentially what we're relying on is the relationship between the temperature of the ocean and the maximum wet bulb temperature on land. Because it turns out that the temperature of the ocean is actually directly sets the maximum wet bulb temperature on land. And that's just because if you imagine it, the water right above the ocean can have 100% humidity at the temperature that the ocean is. And then that's bounded by something that has to do with the buoyancy of the atmosphere. I'm sure Alexey and Mary Louise can explain it to you. Sets the upper bound on what the wet bulb temperature will be on land because of the relationship with the temperature in the ocean and the ability of air to take up water. And so this has been shown in the modern oceans. Matt actually showed it a decade ago in the ancient oceans. And so we're going to rely on that relationship to think about the maximum heat stress on land. So now conveniently, it turns out that when Matt Huber and Sherwood, when they did this paper back in 2010, they actually already modeled a 12°C warmer world. And that's right between our estimates. So back in the Eocene, I said it's at least 10 degrees hotter. It could be as much as like 14. 12 degrees is right in the middle. And if you do that and you model what the wet bulb temperatures are on land, this is what the map looks like. And you can see the key thing to notice is that most of the colors, especially in low latitudes, are above that orange color, right? Pretty much everything is above orange. And so those are all areas that we would project would be very difficult for an endotherm to live in if our estimates based on modern organisms are correct. and if the organisms that live actually are exposed to those temperatures. So behavior has a big role to play here. And so what we're doing is we're trying now to move beyond this one estimate, which is based on one model, by using these multi-model compilations to think about what's going on with heat stress through time. Now I'm going to show you this plot super quickly because it's changing. Ironically, when you compare multiple climate models, certain aspects are consistent, like Alexey was saying, but certain aspects tend to disagree. And what's blowing up our uncertainty right now is HAD-CM3. One model disagrees with all the other models, so we're still trying to figure out what to do with it. But essentially what we're able to do is talk about essentially the maximum wet bulb temperature through time, so we can convert between sea surface ocean temperatures to maximum wet bulb temperatures for any latitudinal band. So this is 30 to 30. And then we can also translate that into the amount of area that's experiencing, the amount of low latitude area that is experiencing those maximum temperatures at any given time. And we can also talk about dry heat stress. So that's this red line. So temperatures above 50 degrees Celsius, but dry heat. And this is much more uncertain because models actually disagree on this aspect much more. All the models tend to give the same wet bulb temperatures because of this atmospheric constraint, but they diverge quite a bit on just dry temperature variation. But we can actually start to move with this towards projecting through time what the surface of the planet looked like in terms of how hot it was during these different environmental states. And we're doing this, of course, because we want to ask, okay, what about life? Right? Like, those are really hot temperatures. Our intuition based on the modern day should say nothing lives there. But of course, I'm looking at Greg. Greg actually goes out and looks at fossils. Greg can tell you there's a ton of fossils in these latitudes back when it's really hot. And so this is a map using the Paleobiology database, which is a big compilation of fossils, both in the ocean and on land. And I asked the Paleobiology database to just show me all the spots that have fossils during the Cenomanian, so about 100 million years ago, and for reptiles. So everything, including everything from lizards to pterosaurs to dinosaurs. And this is the distribution that you get. And if you remember, a lot of these areas, I realize the continental configuration is different, and that does affect climate models. I can get into details like that afterwards because we model it actually with these continents. But they're occurring in the low-lying areas where we expect wet bulb temperatures to be about 10 degrees hotter than the present day. Ooh, no. Sorry, this plot did not come over right. So there's a lot of data here you don't see. It's all nicely color-coded too. So here, it's almost not worth speaking about. We could just go back here, but okay. So this is actually just the mean line. That's the only thing that you're seeing is the mean line here. But essentially what we wanted to say is, okay, we know that there are deposits in low latitudes, but maybe there's like one fossil there, right? How does diversity, how does the number of species that you're finding at these latitudes relate to temperature? And so what we did was we just looked at the deposit by deposit diversity. So something that you could call alpha diversity. How many species are being found in a certain area at a certain time? And when we did that, we saw that there was, and you can see so clearly, there's actually an interesting relationship that as the temperature gets hotter at low paleo latitudes, the diversity of each assemblage actually goes down. There's a lot of error around this because there's so many reasons that make it extremely difficult to get good estimates of diversity from land. But within all the crazy noise, it goes down, whereas the mid and high latitude diversity tends to go up with temperature. So as those latitudes warm, assemblages tend to be more diverse, and as it warms, the tropics really does appear to be less diverse. And now this is just a first quick pass at the data that my former graduate student Jack Shaw did. And I have this wonderful incoming postdoc who is a Donnelly Fellow, and she's going to be putting together very carefully dinosaur assemblages and really looking at their diversity and things like body size and taking into account what we think might be the heterogeneity in the thermal landscape to really ask this question in a better way. So that was the goal of the talk. How hot has the surface been and how did life respond? The key takeaways I want you to have from this talk is that we really do have the data and methods to address this question in a serious way from the fossil record. We can actually give you some constraints on what life can adapt to, and I think we should take it seriously from a modern perspective. When we start to say things like, oh, things will all die when it's 2 degrees hotter, it just doesn't match up with what we know from the long history of life. And so there's a lot of reason to hope for that. There's a lot of things that species can do, like the behavioral adaptations that Marta Munoz, for instance, studies over in EEB that can actually start to mitigate how organisms deal with heat. Another one of my favorite, if anyone wants to give me like $500,000, is thinking about how organisms can avoid the heat by essentially going to sleep. So kind of like the ostrich putting its head in the sand, a lot of organisms basically just dig a deep hole and take a deep nap when it gets nasty, and how these type of behaviors relate to changes in temperature through time is a major question. From a temperature perspective, there's uncertainty, but we can bound that uncertainty and really move forward to think about effects on life. And again, of course, this is very initial results that have gone through very quickly. So there's a lot to do, but we're excited, and I'm excited to talk to you guys all about it. And of course, this is all due to our ability to really look at past oceans and look at past climate states from the bottom of the seafloor. And so my work really depends on 50 years of ocean drilling, which is a hugely collaborative and interactive community that's been going out to sea, since the early 1960s. And so it's heartbreaking for me to tell you that I'm actually going to get emotional here, but on March 6th, they actually pulled funding from the boat. And so we've lost our ability to explore the deep sea. And I think this is catastrophic, actually. Yeah, we have thousands of cores, but for new questions, we can no longer go out to the ocean and look at it. And you can build another boat, but you cannot rebuild the expertise of 50 years of careful training that's been passed down hand to hand between these different drillers. And so to cut off our ability to go to the ocean at this point in time is so short-sighted. And yeah, it may be the UN Decade of the Ocean, but it's not the US Decade of the Ocean. We gave up our ability to go to sea commercially with the merchant marine back in the 80s. We've never been great at the high polar regions. We don't have that many icebreakers. We're giving up our ability to go to the deep sea. So I think it's worth taking a direct look at ourselves and our ability to explore and understand the world, because we're really doing our best to give up the majority of the planet at the moment. So sorry to end on a sad note. I usually am so optimistic, but this one's hard. So this is a huge collaborative work. These are just some of the collaborators that have been involved so far. And thanks so much. Thanks, Kelly.
I was interested in the taking into account of plate tectonics.
Mm-hmm.
Are your data sets taking into account that as you go deeper, things were in different places? And if they don't, how do you think your conclusions might change?
Yeah, we do. So in the last 100 million years, things move like this way a lot. They actually don't move north-south a lot. So that helps. There's a whole field of expertise that reconstructs where plates are through time. And we've actually gotten pretty good at doing that, saying where things are, at least for the last 100 million years. When you want to think about temperature further back in time, I'm like, oh gosh, all bets are off. The proxies get really nasty. The plates get really nasty. But our estimates actually come from back projecting where those individual sites were through time. So we actually back projected them. And when we accounted for things like the salinity of the ocean, we put an uncertainty grid cell around it. We said, okay, it's within this certain area, and we looked at the effect of that uncertainty on the temperature estimate through time.
So you had a slide where you showed that when the temperature went up, the diversity went down in low latitudes,
Mm-hmm.
but the diversity went up in mid and high latitudes.
Yeah.
Do you have maybe a postulation of why the diversity went up?
I do. So that axis that I was showing you on that plot, it's a preliminary plot. We just used our low latitude temperature across all of them. So the reality is that when it's, let's say, 35 in the low latitudes, the average temperature in the mid latitudes is is lower, right? And so we do think that there's a relationship in the modern world between temperature and diversity. Like as it, as you go to warmer and warmer places in the modern world, you see higher and higher levels of diversity. And that relates to things like productivity and the relationship in other factors, like the amount of area at those different latitudes. And so what we think is going on is that that's true to a point. You can imagine an inflection point. As you get warm and warmer, you can imagine systems are more productive, and then it sort of drops off. And we have good reason to think that based on the physiology of how things photosynthesize. So we know that the temperature dependence of respiration is a little bit steeper than that of, let me get this the other way. The temperature dependence of photosynthesis is tighter than it is for respiration. So your photosynthetic capacity actually sort of drops off more rapidly than respiration. So even a plant starts to net respire if it's hot enough. And so you can imagine that the net amount of photosynthesis of carbon that's being fixed actually starts to go down after you reach a certain temperature, which isn't even 30. So the plants start to be less efficient at high temperatures. You can imagine productivity goes down. So instead of just a monotonic line, we think it's actually a curve. Yeah.
Awesome. So, Charlie, how do you think the rates of change in increasing temperature today versus in the past might affect the ability of the, different species to respond?
Yeah, no, I think in the end, it's, I oftentimes when I give this talk, I say it's not the absolute limit, it's the rate of change. So I think we tend to infer that it's the absolute temperature today because it's the rate that's so fast. But if we look to an event like the Paleocene-Eocene thermal maximum, this rapid global warming event 55 million years ago, there is a lot of evidence in the oceans for a decline or even extirpation of organisms from low latitudes. And this is a warming event of about 5 degrees C over, let's say, 2,000 to 5,000 years. So it's an order of magnitude slower than the present day, and yet things appear to be tracking the thermal niches out of the tropics. So they're actually like moving out of the tropics. And so people have argued, oh, it's too hot for life in the tropics during those times. But I'm like, I don't think it's too hot for life. It's not actually hotter than the hottest part of the Cretaceous. I think it's too fast. And so I think you have to shift from absolute thermal limits to rate of change, the climate velocity side of things.
Thanks, Kelly.
Thank you.
I'm Shimon Anisfeld from the YSE, Yale School of the Environment, and thank you, Mary Louise, for inviting me to talk here. I'm going to take us a little closer to home, to Connecticut and salt marshes. Smaller scale and shorter time periods than the last two talks, which were amazing. And what I want to do is talk about in two parts. The first part being sea level rise and its potential negative effects on marshes in terms of submergence, marsh drowning, and then shift to the possibilities for marshes to migrate as upslope as sea level rises. Okay, so starting with some basics, because some people are very familiar with marshes and others aren't. So when I say salt marsh, I'm talking about an intertidal ecosystem where the elevation relative to the tidal frame really determines a lot of stuff. It determines the oxygen availability, it determines plant communities, it determines types of respiration and so on. So this is the classic picture of a Connecticut salt marsh or New England salt marsh more broadly, where you divide it into zones: low marsh, high marsh, upland border, all by elevation relative to the tides. And you could kind of see this donation pretty clearly in the field. You've got the high marsh zone. I guess I do have a pointer here, huh? You've got the high marsh zone here. You've got what's sometimes called the blackgrass zone for obvious reasons, Juncus gerardii, and then a Phragmites fringe behind it, and behind it the upland. You can quantify this if you want to. This is from Connecticut, all across Connecticut, different marshes, looking at where these species are in the tidal frame. So elevation relative to, oops, wrong one. Elevation relative to mean high water So Spartina alterniflora is the characteristic plant of the low marsh. And it's actually got, if you can see here, it's got quite a large range elevation-wise. I mean, large from a salt marsh perspective. It can grow over, maybe a meter of elevation range. That's a lot in a marsh. Because the low marsh tends to be sloping. The high marsh, in contrast, we've got pretty tight elevation here. It's a pretty flat platform. And then you got the upland border. And of course, these elevations correspond to flooding frequencies and durations, right? That's what I mean when I say hydroperiod. So the low marsh is flooded on most tides, not every tide, flooded on about 3/4 of tides. And it's flooded for about 1/4 of the time. So if you go to a low marsh at low tide, it'll be dry, but just think, of course, it's flooded about 1/4 of the time. And my screen disappeared. Okay, there it is. And of course, you got to remember that high tide and low tide vary, right? So we've got this spring neap cycle and this higher and lower tides within each day, which creates this complex dynamic of elevations over the course of a month, of course of a year, of course of a 19-year tidal epoch, which is what allows these elevations to be flooded sometimes and not other times, right? Okay, so that's the first point. We've got this ecosystem that's pretty sensitive to its elevation relative to sea level. Second piece is, of course, sea level is rising, and it's rising at really fast rates, at least in the relatively small time frame that I look at, which is a couple thousand years. So we know this from a lot of places, but we know this from Connecticut also. This is basal peat samples. So marshes can actually tell you about sea level rise, of course. So this is from one site in Guilford, looking at relative sea level change over the last 2,200 years. So when I say relative sea level change, I'm looking at how sea level is changing relative to the land, right? But of course, around here, the land is generally sinking, right? We've got this post-glacial rebound from the post-glacial changes, and we're actually here experiencing a collapse. We're in the forebold, which is collapsing. So we're experiencing a glacial isostatic adjustment of about 1 millimeter a year. So that's kind of the baseline. If global sea level is not changing at all, well, Connecticut is sinking by 1 millimeter a year, so therefore it's experiencing relative sea level change of about 1 millimeter a year. Right? Okay, so that's what we have for most of the last 2,200 years. We have the little ice age, a little bit of a dip in that, and then we have acceleration to modern rates of sea level rise, which includes still that land component, right? Land sinking by 1 millimeter a year, but clearly lots of other ocean effects on top of that to about 3 or 4 millimeters a year now. And of course, we can kind of look at larger data sets beyond Connecticut to understand this and understand that this is driven mostly by the fact that the ocean is warming, its density is decreasing, and the fact that there's more water, more mass in the oceans because of glaciers melting. And of course, we know that this, as the oceans continue to warm, as we continue to lose glaciers, as we lose ice from Greenland and Antarctica, sea level rise is going to continue, with its rate being dependent, of course, on which of these SSPs that Alexey was talking about we follow. And you can also see, of course, sea level rise is not uniform across the oceans. It has hot spots and cold spots, both because of temperature changes and also because of other circulation effects and land effects and so on. And we happen to be, in a pretty hot spot of sea level rise. Okay, so we've got, on the one hand, an ecosystem which is very dependent on its position. On the other hand, that is changing, right? So what's really interesting about marshes is that they can adjust to their elevation to the rate of sea level rise. Marsh grasses are often thought of as ecosystem engineers. They create their own habitat. And the way they do that, of course, is by trapping sediment. And so as it gets wetter, they trap more sediment and they raise their position within the tidal frame. So this is a schematic. This is not data, but a schematic of how this works. Essentially, if you go out to a marsh and you look at the sediment, you take a sediment core, it's a peat, right? It's got a lot of organic matter, and it's also got inorganic sediment delivered by the tides. And the logic that's expressed in this graph is that as you get wetter, as sea level rise accelerates, you get wetter, you get lower in the tidal frame, there's more opportunity for sediment to come in because you're underwater more of the time. And we know this because low marshes have more sediment coming in than high marshes, right? So that kind of makes sense. So this mineral contribution goes up. And the organic contribution also goes up to a point, right? So as it gets wetter, there's more organic matter preservation. And for a lot of marsh plants, actually wetter is more productive. So that they prefer to be a little wetter. That wetness will increase productivity, both above ground and especially below ground, where you've got roots and rhizomes and organic matter contributing to the growth of the peat, right? But only up to a point, right? At some point it gets too wet and the plants die and then the whole thing collapses, right? Okay, so just some data from Connecticut and a couple New York marshes thrown in to show that this is in fact happening. So this is across 14 marshes over the last century, essentially, looking at how marsh accretion, the rate of increase of marsh elevation over time, has changed. And what we're seeing is that you can see if you look at this marsh surface, it's rising over time, but the rate of rise is accelerating, right? So as sea level has increased over the last century, the marsh is also growing more rapidly, but it's not quite keeping up, right? It's got a lag. If they started out, kind of at the same elevation, which obviously isn't quite right, but putting it relative to 1900, the marsh on average has lost 5 to 10 centimeters of elevation relative to sea level. So it's gotten lower in the tidal frame, but it's accreting more rapidly. So there is this response. It's not quite enough, but it is increasing its accretion rate. Where's that coming from? Well, it's coming from both inorganic sediment and organic sediment. This is the organic piece of it, which is the larger piece of it. So as these marshes get wetter, they accumulate more and more organic matter. That's blue carbon, right? So it's both taking carbon out of the atmosphere and storing it in the peat and allowing the marsh to maintain its elevation. Not quite maintain its elevation, but close. On the other hand, there are certainly places you can go to in Connecticut where marshes are being submerged, getting too wet, crossing that boundary point where the negative feedback loop switches to a positive feedback loop, and wetness decreases your ability to accrete. And this is an example, Sherwood Island State Park in western Long Island Sound. You can see all these areas in here that are not vegetated now, all used to be vegetated. And in the last few decades, they've lost vegetation. And, I should have maybe started with this, but we care about this for lots of reasons. I mean, one of them is habitat for this salt marsh sparrow, which is kind of getting pushed between sea level rise, decreasing, leading to submergence, and some limits, like houses here, to its ability to move upslope. So we care about it in terms of habitat. We care about it in terms of coastal protection, in terms of the ability of these ecosystems to attenuate waves, reduce storm surges and stuff like that. And if you think about it just from a carbon perspective, of course, all that blue carbon is now being lost, right? So it's not accreting anymore. It's actually all the organic matter in there is decomposing, right? This is not about sea level rise, but I thought I would take the opportunity to say that there is also other stuff going on in Connecticut salt marshes. So, sea level rise and climate change are happening in addition, of course, to other anthropogenic impacts on these systems. And one of these actually has to do with a cute little crab called the purple marsh crab, or Sesarma reticulatum. And it's a native crab to Connecticut salt marshes, but it has increased in population in at least some marshes. And the thinking is that it's a trophic cascade, essentially, that a lot of its predators, like green crabs, blue crabs, some fish, have been overfished by people. So you get this classic trophic cascade where the negative impact of people on, let's say, blue crabs, not shown here, but blue crabs, has actually a positive effect on Sesarma, which increases its population, which then creates a problem for the marsh grasses because Sesarma digs these burrows, undermines the marsh plants, and actually eats marsh plants as well. So marsh plants as well. So we thought it would be interesting to go out to a couple marshes where we thought, where at both sites, marsh loss was happening, and we thought we could diagnose different phenomena here. And if you look at it, it seems pretty clear, and these are just two sites not far from here. I think I just turned that off. Okay. A site here where you can see this kind of extensive mudflat forming, which is just kind of low-lying and wet and seems to just be too wet to support vegetation. We'll call that submergence. And you see this other site where the characteristic signature here is this herbivory on the creek banks. You can see these burrows. You can actually see a lot of marsh crabs. They're kind of hard to see during the day, but you can catch them. You can trap them. So we thought pretty clearly these were on the surface, just look at it from aerial photos. This is both marsh loss, but they're really different things going on here. And we kind of established that using transplants and cages to protect the transplants from crabs, and essentially establish it. Yes, we can identify two different phenomena here. Okay, so that's the piece on the kind of loss and the threats on the seaward end to marshes in Connecticut. And really, essentially what we're talking about here is the movement of this lower boundary upslope, right? So the low marsh is the first to go. It's the wettest. It gets too wet to support vegetation when it can't keep up with the rate of sea level rise. But if we really think this is happening, kind of upslope movement here, then we should also be thinking about upslope movement there, right? We should be thinking about marshes replacing coastal forests, whatever that upland is, as sea level rises, colonizing new territory. So that's where I want to turn to for the second half of the talk. So we know marshes can migrate upslope. I mean, you certainly know from the geologic record that marshes move over time, but we also can see it happening in real time. We see it in the form of ghost forests, where you see there used to be living trees here. These trees are dead. We have upper marsh shrubs coming in under this. So this clearly is a marsh where there used to be a forest. You could do aerial photo analysis and kind of quantify how quickly marshes move upslope. This is an interesting case in Delaware Bay where what happens is the forest retreats, right, as sea level starts to inundate the forest. Salt marsh takes over, but actually what really takes over is Phragmites, this non-native reed that is, ends up occupying a lot of this space, which you could call it part of a marsh, but it doesn't provide, at least arguably doesn't provide the same habitat value as a native salt marsh. So, taking you to just another piece of research that we've looked at in Connecticut here, we were trying to think about ways that you could assess migration outside of looking at aerial photos, because aerial photos are not always available and interpreting them can be tricky. I mean, sometimes you got a clear forest and a clear marsh, but there are cases where you might say there's maybe invisible migration happening, like a marsh moving under a forest, or in other cases, which we could discuss later. So we went, of course, to looking at the sediment signature of migration. And we went to foraminifera, the same animals that Shelley was talking about, because they're very characteristic of marine environments, right? So we're pretty confident that when we see foraminifera, we're looking at a marsh. Whereas where we don't see foraminifera, when we're in an upland, we don't have foraminifera. So the idea was here to try to recreate the migration of a marsh over the last 50 or, over the last few decades, a pretty small time period, by looking at the signature of marsh sediment, right? So if you imagine this, I'm hitting the wrong one. If you imagine this simply as the pre-existing slope of the marsh bordering community, you would imagine that over time, as the marsh moves upslope, it starts to accrete sediment, and you get this wedge of sediment. And then the question is, how do you identify that sediment? And a lot of people have gone to looking at organic matter as a signature of a marsh, right? Because marshes, these peats are highly organic. But we were kind of worried about that because if you think about it, the signature of organic matter moves down over time, right? Roots and rhizomes grow 20 centimeters into the peat, which might be fine if you're looking at, multi-thousand-year timescales. But if you're looking at decades, that's that's really misleading in the sense that this, which now looks like a marsh, was originally an upland. This thin layer here is what accreted on top of it. So we wanted something that wouldn't move over time. We came up with foraminifera. And so we went to 2 marshes in Connecticut and were able to essentially take cores and essentially quantify that wedge. So the idea is here we have this, we believe, is the pre-existing slope of the pre-existing upland. Over that, we have a wedge of marsh sediment with forams present here and forams absent here. So we can see that marsh moving upslope, and we can quantify it based on cesium-137, based on this marker for the year 1963, atmospheric deposition of cesium-137, which, if you look at it, in this part, the lower part of the wedge, that cesium is falling on the marsh. In the upper part of the wedge, the cesium is falling on the upland, right? So we know 1963 is somewhere in here. Does that make sense? So it's kind of same idea here. We've got cesium falling into the marsh here, so we know that this was marsh in 1963. Up here, the cesium is falling on the pre-existing upland surface, so we know that was upland in 1963. So that allows us to essentially quantify the rate of migration. We're not looking at vegetation, right? We're looking at the sediment that reflective of a salt marsh, but we can quantify migration in that way. And what's interesting, we only did this at 2 sites. These sites are quite different in terms of their pre-existing slopes, which you might imagine would determine the rate of migration. And in fact, at one site, we essentially, in this 50-year period, we have 50 meters of horizontal migration. The other site, we only have a couple meters of horizontal migration, partly driven by slope, partly driven by other phenomena that we don't understand. Okay, so the last thing I want to talk about is, we know marshes can migrate, but I want to just think kind of broadly about the limits to that, the barriers that prevent marshes from moving upslope. And I'll talk about three barriers that we can identify. And the first is kind of obvious. It's a topographic barrier, which is that if the slope is very steep, there's just not a lot of land that gets occupied as sea level rises. And this is a marsh that's familiar to some of us, Hoadley Creek. And it's like a lot of Connecticut marshes. It's kind of a pocket marsh because of our glacial geography. We've got a lot of bedrock outcrops right along the coast, right? So what you have here is a marsh in yellow that's essentially occupying all the available space. And as sea level rises, let's say by 2055, projected what areas can become new marsh. You're looking now at the dark green, high probability of becoming new marsh. This is just a model based on topography. What areas will now become intertidal, essentially. And there's just not a lot of area, right? Just really little fringes here and there. And that's simply because it's a steep site. There's, you got bedrock outcrops preventing the marsh from expanding. So pretty simple. And that's, not the case like in Delaware Bay, right? But it is the case for a lot of Connecticut marshes. So there's a limit, even under the most optimistic scenarios, there's a limit to the amount of space that's available in this intertidal range under sea level rise projections. There also, of course, are anthropogenic barriers, right? So we've tended to develop right up to the coast, right up to these marshes. So what the marshes are moving into tends to be things like parking lots, roads, campgrounds. This is a state park that gets up around 1 million visitors a year, believe it or not, and filled with RVs in the summer. And this is essentially marsh, right? So this is where the marsh is migrating into. This is a particularly high tide event, but the marsh is taking over the campsite essentially. And we have the same phenomena at other state parks. This is Sherwood Island State Park in Western Connecticut. Here, again, this is an area that is essentially now should be marsh, but is being mowed. In this case, not for campgrounds, but for a model airplane field. So there's lots of kind of competing uses for this space, and kind of the ecological values of marsh migration aren't necessarily foremost on managers' mind. And you can see, actually, if you look closely, you can see they're actually mowing blackgrass. They're mowing Juncus gerardii, a marsh plant. And it's getting harder and harder to mow every year as it gets wetter, but they're persisting. But we're able to persuade marsh managers, park managers at both these sites and one other site in Connecticut to stop mowing in certain areas, these no-mow zones, and you can kind of see what happens. Of course, marsh shrubs come in. Not the best picture, but this is one of the no-mow zones, kind of extending from low to high. This is all marsh here, flooded at high tide. It's an unusual flooding event. And then this is what the mowed area still looks like. And that, of course, allows the marsh to become marsh. So we have topographic barriers, we have anthropogenic barriers. Maybe the most interesting category are ecological barriers, recognizing that if a marsh is migrating into a coastal forest, that forest has some resilience to that migration, has some resilience to sea level rise. From the forest perspective, we think of it as resilience. From the marsh perspective, I would think of it as a barrier. And that's been thought about for a while. A 1995 paper kind of laid out a model for how this happens, these changes from an upland to a high marsh or from a high marsh to a low marsh and so on, driven by intrusion of brackish water, right? So sea level rise and salt water moving upslope is what's driving this, but also some factors that resist that change. And in particular, shading, right? So marsh plants generally don't like shading. And so it's not simple for a marsh plant to move under an existing forest. It takes a while for the trees to die, right? Even under the best conditions of brackish water intrusion. So there's a gap there in terms of timing. There also are other factors like, is there fresh groundwater being discharged? How does the interaction of the upslope hydrology and the tidal hydrology affect the salinity? So that's one way of looking at it. Kind of more recently, there's this ecological ratchet idea, recognizing that actually there are two things going on here really at the same time. There's a press stressor to the coastal forest, which is sea level rise year after year, a little more salt water getting upslope. But you also have storms, right, which are a big pulse of salt water and a lot of wind, so potentially lots of sources of damage to the coastal forest, creating an opening for marshes to move upslope. So one way to think of it, I'm not totally convinced that this is reality, but one way to think of it is to recognize there's actually two boundaries here, right? So there's the boundary that we kind of see pretty clearly between the marsh and the coastal forest. But within the coastal forest, there's an area that's bordering the marsh. It's a little more stressed. Maybe there's no regeneration happening, right? So adult trees are surviving, but there's no regeneration. Upslope from that, you have an area that's not yet seeing the stress of saltwater, and is a healthy coastal forest. And what this is suggesting is that each of those boundaries is driven by a different phenomena, that sea level rise slowly moving upslope affects regeneration, but what kills the trees in the persistence zone are these storm events. Right. So I'll end with another little piece of research here on trying to understand the role of storms in coastal forest die-off, which I'm still involved in. So we're still working on with Craig Broderson, a colleague at YSE, and Carolyn Salvadelli, who an MESC student who graduated last year. And essentially at Barn Island, there's a huge amount in eastern Connecticut. There's a huge amount of salt marsh. And there's also some coastal forest. So we identified two stands in particular that were interesting. You can see there's also a lot of anthropogenic modification here too. There's paths and dikes and stuff like that. But this is all salt marsh. And this is a stand of Nyssa sylvatica, black tupelo, bordering the marsh. It looks like that. And what's interesting about this photo was taken right after a windstorm, which actually blew all the leaves off of the exterior trees, the ones that are right on the border of the marsh. These are actually living trees here. They just suffered an event. And behind them, you can see the trees that do have their leaves on. And you can also see the marsh plants really moving upslope into this coastal forest. So that's one stand. The second stand is a white oak stand, surrounded by marsh, and you can kind of see the marsh kind of coming at it from all sides. So we were interested in if we could understand in particular the role of storm events in affecting the health of the trees and thus the ability of the marsh to move upslope. We did some other things here too, but I'm going to focus just briefly on what we got from elevation measurements and tree rings. So the idea of the tree rings is to construct a chronology of tree growth over the last 80 years or so and understand how storm events affected the health of the trees. So what would we expect here? So we were able to kind of tie in the elevations of these trees to the tidal hydrology. We defined two types of trees. I don't know if I already said that. Exterior trees, interior trees, they're all living, right? So these don't count. We looked at these two, but just the exterior would be the ring outside. In this photo, obviously the exterior are these trees here, versus interior ones, which maybe represent the regeneration zone in the terminology of the ecological ratchet. We know their elevations. We can kind of, using nearby tide gauges and correcting for local hydrology, we can kind of reconstruct how often they're flooded over the since 1938. So what I take from this is that flooding is not an unusual event for these trees, right? So when I say flooding, I'm talking about not freshwater flooding. I'm talking about, tidal flooding. Tidal flooding is not an unusual event for these trees. Certainly for the exterior trees, they're flooded pretty frequently. I mean, this is over a long time period, but flooding is not like a one-time event. You do see, though, on top of that, you see these storm events, right? Like, so this is Sandy, for example, Hurricane Sandy, Superstorm Sandy. So there are both sort of smaller scale flood events and larger scale catastrophic events, let's say. So clearly it's not just about being flooded. These trees can survive being flooded. It's about the depth of flooding, the duration, the frequency, and the wind that comes with it, which obviously we can't really get at here. So if you just let's say, what do the largest events do? Pick the largest events on here, the real hurricanes that brought salt water way upslope. And you look at those and you look at their effect on tree growth. This is something called a superposed epoch analysis. It basically defines events. And in this case, it's like the 5 largest storm events and says, do the trees consistently respond to those events in terms of their growth? And the answer here is yes. They respond essentially 2 years later. So there's a time lag with a decrease in growth. So this is for all tree rings, meaning both exterior and interior, and the 5 largest storms. So there's some impact. But what I think is interesting is that impact gets larger for the exterior trees, as you would expect, and it's largest for the growing season storms. So I think one thing that we haven't really thought enough about is the fact that if you get a storm like Sandy coming at the end of October, when the tree is not really doing a lot, by the time the tree starts growing in the spring, all that salt water has washed out, right? So we actually find that even though we started this thinking about Sandy, that Hurricane Donna, which happened to be earlier in the growing season, in early September, actually had a much larger effect on these trees. Of course, they recovered, but had a much larger effect than Sandy. Anyway, so that's where we're going. I have a lot more questions about migration. I'm not going to lay them out here, but just wanted to share where we are in that project as well. So thanks to all my collaborators on this. Thanks to Sea Grant for funding. And if there's time, I'll take some questions.
Oh, everyone's hearing the tinking of the glasses out there. Let's go.
Hello.
Hi.
So I don't know if this is maybe a little like simplifying something, but so the marshes are going upslope, is there more concern for what that means for the marsh habitat since they can only go so far because of houses and stuff? Or are we also worried about like the forests that are getting overtaken?
Right. Well, I'm a marsh guy, so I would prefer to see a marsh rather than a forest. So But I think kind of more broadly, these coastal forests they're also threatened, but I think marshes are more scarce and they can only occupy this really narrow habitat zone. So I think where possible, and there are species that are dependent only on, having high marsh to nest in. So I think generally, at least in Connecticut, it's seen as a net positive if marshes do compensate for their losses at the seaward end by moving upslope. But forest people may have a different perspective on that.
Yeah, I'm wondering if you've looked at the impact of invasives and those that have thrived in places where salt marsh grass has thrived before, and also the anthropogenic phenomenon of sandy beach building, which goes on and on and on.
Yeah.
Tens of thousands of tons of sand being brought in from faraway places and putting beaches where there was once marsh.
Right. Yeah.
You've been looking at that?
Well, I mean, it's certainly all these things are threats. I will say the greatest losses of marshes in New England until the 60s or 70s were certainly from things like dredging, marinas, piers, beaches, et cetera, et cetera. That doesn't happen anymore. We now have marsh protection, so now it's more indirect threats. Invasives, certainly an issue. I mean, Phragmites as a classic example. And certainly there is some concern that if marsh migration means more fringe, it might mean more Phragmites. That's not necessarily a good thing. But we haven't seen that at our sites. We haven't seen a lot of Phragmites in these bordering areas. I'm not quite sure why, but.
A sort of practical question. So there is this farm not far from here, Medlin Farms. I don't know.
Yeah.
They grow these nice tomatoes.
I'm going to let Pete come up and talk about it.
There was all the signs save Medlin Farms. And they're very, very close. They basically rolled down the road from the marshes.
Yeah.
And I wonder what's the future for such farms from all the sea level rise.
Yeah. Well, Pete can talk more about this, but I mean, I think kind of broadly speaking, we shouldn't be sacrificing marshes for farmland in intertidal zone. We shouldn't be protecting farmland in the intertidal in Connecticut. We should be allowing farms to move upslope while marshes move into those areas. I know that's not so simple. I know farmland in Connecticut is endangered, but to me, there's a higher value for because salt marshes again can only occupy that narrow zone. Those farms are going to go away at some point. Saltwater intrusion is happening, right? And there's a limit to how much we can protect those farms from that. And we shouldn't be investing a lot in that. That's my opinion. But Pete, do you want to answer what's going on with that?
Well, the Brantford Land Trust did buy Medlin Farm, and part of the funding for that was from DEEP to allow for some marsh migration. And but it's only a small section of the farm that is, not steep enough, as Shimmy was saying, to allow for that migration. And so it's not certain what's going to happen. We're actually putting in a grant. That's what I was just working on, to try to get a management plan to see what people want to do with the farm. And there's a bunch of folks who would like to see it remain too. Yeah.
Thank you.
Okay, well, let's thank Shimmy again.